Find a way to say that better. Okay, 2 to the radical x plus 1. Domain? Shall we? Domain it? This is where domain gets interesting. D, domain. You look at the originals. You realize the domain on g of x is definitely restricted. It's we did it before. It's -1 to infinity, including -1. It's basically any number bigger than -1. 2 to the x, that is all reals. It's the exponential function that we graphed yesterday. It has x can be anything. So the domain on that one's all real. The actual function that we have to pay attention to is the input function. That one, we consider the input function, and we consider the whole composite function. And together we say, all right, what's our domain going to be? We start with the input function. We got its domain. This one right here. You know what I'm saying? Should I get the yellow out here? This is the input function. It's got a domain of -1 to infinity. Our output, our composite function, is 2 to the radical x plus 1. Now we need to consider its domain. And if I look at it, the only thing in that domain issue is the same radical x plus 1. Its domain, the one thing that holds it back, is the same radical x plus 1, which we know means x has to be -1 to infinity. And I want a green. Let's fix that. Green, come on. The law is this, and let me show you the sheet that I would recommend, and we'll take a peek at. Here's the deal with domain of a composite function consists of 2 steps. See up on the big screen? One, it says find the domain of the inside or input function. If you have any restrictions there, like we did, it has to be greater than or equal to -1. Keep it. It says keep them. Then it says step 2, construct the composite function, and the domain of this new function, you simply add those restrictions to the ones you already have. Well, this 2 to the x radical x plus 1 doesn't add any restrictions. It has the same ones. So we just keep the same domain restriction, -1 to infinity. You start with the inside function, move to the outside. This lovely little sheet here, ultimately, if I get my little highlighter going in here, let me find it. Where are you, highlighter? I can do this. I can do this. I think it's, I don't know where it is. Oh, there it is. Ta-da! This, down at the bottom, the domain of the composite function, oh, there you go, is determined only by the composite function. So that's what we got. That's a big deal. But you consider the input function first to kind of get the ball rolling, and then you say, all right, now look at the composite. What new restrictions might I have? Interesting thing about the composite function, it might have a domain that looks totally different than the ones that made it. Your domain there might be something totally new. Okay, so, but we're default in the end of the composite function itself. All real. All right, to the bottom here. Decomposing of functions. These things are rank. I mean, look at this. Just steam, gooey, decomposition. Why does it stink? Is it methane that makes stinky stuff? Bacteria creates methane gas, and that makes things that are decomposing stinky. Anyone doing biology stuff? Must be making this up. Anyway, here's my question for you. If I've got an f and g that are stuck somehow together, and the result h of x is this, I'd like to know what f and g are. You have any ideas? Anyone want to look at that? You could be the hero. By the way, there's more than one answer. Did you know you can't see anything I'm writing? See that? What could f and g be? If you have a guess, you just want to put it out there. Hint. Do you want a hint or somebody got one? Ready, Sydney? Go.
Oh, no, it's not a hint. Why did we just skip those?
We skipped two functions? We did?
We skipped 2i, 3i.
Oh, I'll come back to those. That's fine. Let's just call this a break. And then we'll go back. Thanks for pointing that out. Let's take a little break and say, what would G and F maybe be? What if G of X were X squared? What would F have to be?
I got an answer for this one.
Abe is on. Okay, go Abe.
Without the x squared.
Okay. Go for it. I'll change it. You just tell me.
Okay. F of x was x.
Okay.
And then g of x would just be square root of x squared plus 5.
Oh, that's so simple. It's clever. You are so right. Isn't that cool? That's one option. Simple and clever. Anyone have another one?
How do you even get that?
All right, so up above, do you see the f of x? Or this is h of x over here. It is made of f of g of x. So g of x is stuck inside f of x to make h of x. I have h of x. So what we're doing now is we're like going back going, oh, what are the two functions you put together to make this happen? I did take attendance, right? Hi, Ellen. He is, yes. He has should have a tardy next to his name. I don't know. He disappeared something. Oh, thank you very much. You bet. Bye-bye. Sorry. We had you marked somewhere else. Unless you came in before, I don't know. We'll figure it out. G of x, give me another suggestion. Oh, come on. What else you got? What would f of x have to be in this case? So what happens is, I'm looking for what are f and g of x if I know g of x goes inside f of x to make h of x. So according to this, if I put x squared into f of x where x is, would that give me h of x? And yes, that's one possibility. If I take g of x right here, put it inside f of x where x is, would I get h of x over here? Yes. Those are two possibilities, and they're not the only ones. You can come up with many. But the idea is you can decompose and find out what maybe the composite functions were as well. So, isn't that kind of cool? Pull it apart, decompose. It's a great word. The other thing that comes to mind are zombies. Zombie Burger. Oh, like that place. Isn't that fun? Did I hear you hate Zombie Burger? Oh, I thought maybe you were scared of it or something. All right.
And then I forgot I wanted it, so I drove all the way down.
That's tough.
I know I did.
All right, folks. G of f of x. I took f of x. I put it into g of x where x is located, and I got the following. Okay, I got that in there. The results, I want to know its domain. Now, the input function f of x hath no restriction on the domain. So now all we have to look at is just look at the composite function for its domain. And the only thing that kind of comes to mind is, hey, just make sure the insides are never, ever less than 0. And the way we work that out is we do a little solving. We actually say 2 to the x plus 1. It's got to be greater than or equal to 0. And we solve it and try and find x. Or, you super sleuths, tell me about 2 to the x plus 1. If this is 2 to the x, it's always positive. 2 to the x is already positive. If I do plus 1, it's just up 1. It's still positive. We are totally good. That domain, this 2 to the x plus 1 is greater than 0 all the time. So the domain on this one, all real. So you look at the internal function, see what it can tell you, then you look at the composite. That's ultimately your decision maker on the domain. All right, we're going to do number 3. Man, we were so close to skipping these. Now we're back here doing this stuff. Thanks, Sydney. Whole bunch of more work for me. It's good for me. Thank you. Sincere thank you. We needed this. So f of g of 3. Got him. I'm going to get g of 3 first. So that means radical 3 plus 1, which is radical 4, which is 2. I'm going to put that into f here. Y'all see what I'm saying? That this g of 3 is 2, so I put a 2 there. End result, 4. That's basic composite functions and their domains. What do you think? Can you lob some good ones at me? Go for it, Sydney. Yeah, okay, let's talk about domain on that one. This actually, I was going to kind of leave it till we got to a more obvious graph. Our composite is this. If it equals 4, that's a horizontal line. And the domain of a horizontal line is all real numbers. Because any x. But the interesting thing is I don't really have a place to put in x. So kind of, it's a horizontal line. So you'd say domain is all real numbers, but we don't really have a place to put any x. So we'll talk about that more in another example like that. But yeah, it would be all real if somebody asked. Good call. Next, keep rolling. We've got ourselves implicitly defined functions. So down below, the general term for a set of ordered pairs is called a relation. In green, if the relation happens to relate a single value of y for each input x, it is called a function. That's all. Relations are xy order pairs that make a graph. Function is specifically means it passes the vertical line test. There's one output for every input. Pretty cool. So is x squared plus y squared equals 4? Does that make a function? Do you know what this is? What kind of graph is that?
Circle.
It's a circle. You remembered. Good job. It is a circle with a radius of 2, since this is r squared. 4 is r squared. So in the end, you have this little graph that goes, I do 2 to the left, 2 to the right, 2 above, 2 below, draw a circle. That is gross. But it's a circle with radius 2. Just take my word for it. Is it a function? No. Vertical line test. What is the graph? Circle. Solve for y. Okay. I will. You want to know why? It's because it's fun. Y squared equals 4 minus x squared. Take the square root. We'll find what we see. It'll be the square root of 4 minus x squared. Don't forget, it has to have plus or minus. Because you do radical, and that's what happens. Subtracted x squared. Square rooted. And then you check Twitter really fast. You say the relation is given by the equation x squared plus y squared equals 4, or you could say it's y equals plus or minus radical 4 minus x squared. All that I'm asking now, hey, do you want to go back to something we learned a long time ago? What can you tell me about a even power of y greater than 1 with respect to, is it a function? Do you remember that rule? It's the rule of thumb. If you have an even power of y greater than 1, is it a function or no? No. So that's actually